The UNIGINE Landscape Terrain System provides advanced simulation of terrain, a crucial object in outdoor scenes. It allows reconstructing virtually any arbitrary landscape. The terrain is optimized for use with centimeter range resolution data and supports large-scale distances. Combined with asynchronous data streaming and adaptive hardware tessellation, this system is capable of streaming and rendering details up to 1 millimeter per pixel with support for zooming. Independent layer system makes it convenient for development of terrains featuring real-time geometry deformation and simultaneous editing by a team of 3D artists. The landscape terrain system features also multi-purpose landscape masks and support for decal-based holes. Please note that in order to simulate overhangs and caves, you should use static meshes. The landscape terrain system is represented by two objects. Landscape terrain object is an infinite plane responsible for rendering geometry and graphic data, as well as for physical calculations. Landscape layer maps are rectangular terrain layers that store graphic data for height, albedo, and 20 multi-purpose single-channel masks. By arranging and blending them, you can compose a complex terrain in convenient manner. So let's start and create a landscape terrain in a default world. Turn off the ground plane as we're going to have another ground. Press Shift and right mouse button to open the Create menu. Choose Landscape, Landscape Terrain, and click somewhere in the viewport. A new landscape terrain object with a single landscape layer map is added to the scene. You can't transform the landscape terrain. It stores general settings and represents an infinite size container for layer maps, each having its own transformation and bounds. A layer map is a rectangular terrain layer of a certain size, flat and white by default. Let's make it a bit darker. The default size of the layer is 1 by 1 kilometer. You can adjust it using manipulators and the input fields for width and length. The landscape parameter refers to an LMAP asset that stores the graphic data of the layer. It is read-only by default, so we need to create a new one using this plus button to make changes. As you can see, a new landscape layer map asset is added. Let's call it Base Layer. The asset has multiple import settings, which are prompted to the layer map node parameters for convenience. In data filling, you will find two options for terrain creation. You can either sculpt from scratch using brushes or generate a landscape based on textures created in third-party software. If we choose manual, we'll have to specify data resolution and blending mode for each map. The latter can be skipped since we've got only one terrain layer. Click Re-import to apply changes. Remember that re-importing resets all manual modifications made to the layer before. Okay, here we go. You can see the current data density, which is simply the layer spatial size divided by the data resolution. Let's get to sculpting. In the brush editor, you can choose one or several layer textures to paint on. Choose the tool, for example, the brush tool, hotkey B, and select a brush. Here you can adjust settings for the current brush. Its size, use the mouse wheel to do it quickly, spacing between the brush marks in a stroke, opacity, color, and others. Now you can paint over the height map by dragging the mouse holding its left button pressed. By choosing the additive height blending mode, you will add the specified height value atop the surface. Undo and redo are available per each stroke. Hold the Control key to invert the height value and lower the terrain surface. In the Alpha Blend mode, the brush marks override height values. We can set the desired height to flatten the surface and create plateaus. Left-click with the Alt key over terrain to pick the height at a certain point and use it. For complex shapes, you can create a custom brush and save it as a brush asset and specify the opacity mask for it. Change the angle to adjust brush rotation. The eraser tool, available via E hotkey, simply resets the height, albedo, or mask values to 0. Use the Smooth tool for gradual transition and blurred details. The Radius parameter defines the blur radius. The same way, you can modify albedo using a brush with a selected color. or a specified texture. This is how the basic look of the terrain is made. You can also modify 20 multi-purpose masks to apply details. We'll consider them a bit later. Once you've finished, close the brush editor. The modifications will be kept in the layer map asset. For quick height adjustment, use the height scale parameter. You're also free to transform the layer map as you need. Move, change its size, or rotate, but only around the Z-axis. The key point here is that transforming layer maps is not the same as transforming ordinary objects like meshes. All graphic data has to be reloaded so the transformations are not applied instantly. Reloading time depends on layer size, data density, and streaming settings, as well as on your computer's capabilities. You can also create a terrain using textures made in a third-party terrain generation tool. To do so, select from Tile Set from the Data Filling dropdown. As data sources, you can use either assets or files outside the project's data folder in case your terrain is large. Flip tiles along the Y-axis. If necessary, choose the desired data resolution, or keep it detected automatically. The data source can be represented either as a single raster image or as a set of images called tile set. The next section is applicable to the naming of tiles inside the tile set. Proper configuration is required for tile sets to be detected automatically. 2 tile set layouts are supported. The row column naming type is for images having X and Y indices in their name, while index tiles are enumerated with a single index. For this type of layout, the number of columns is to be specified. Make sure to specify the pattern matching if your tiles are named in a special manner, other than the default pattern. The order of tiles in a tile set is specified via the horizontal and vertical order parameters. By default, the tiles for the terrain layer are taken horizontally and then vertically. To change the order, toggle the transpose option on. Data sources are specified in the Import Map section, starting with the height map. You can skip height map data by choosing None, select Only Height Map, or use an additional height opacity mask, which is pretty useful for blending layers. Any grayscale or single-channel raster image can be used as a height map. However, the best option is to use 16 or 32-bit depth image formats, such as EXR and TIFF. Otherwise, the density for the landscape surface may be insufficient. In case of using a tile set, you only need to specify the first file. Others will be added automatically according to the naming pattern. The data can be used as is, or can be normalized to the range between the minimum and maximum height. Let's set the highest point of the terrain to 1.5 kilometer. You can also select blending mode to configure mixing with underlying terrain layers. The next data source is albedo. We also don't need the opacity mask here. When importing a texture, simply select the albedo preset for convenience. The albedo map has 2 more blending modes, which are quite straightforward. The next section enables you to specify 20 terrain masks, which can be used for different purposes. Define the areas for terrain details and vegetation, or as land classification maps. Here you can specify the splat maps of your terrain. Each mask has a name synchronized with the current landscape terrain object in the scene. A mask is a single-channel raster image. You can either import such a texture with the corresponding preset, or use an arbitrary RGBA texture and select a channel to be used. You don't have to specify or disable all the masks. By default, each mask is filled with black color, so you can leave the ones you don't plan to use as they are. Click Re-import for the data to load. Here it goes. The albedo and height maps from the basic look of the terrain. Normals are calculated automatically based on the height map. The current data density value corresponds to the biggest texture or tile set used. Landscape masks are invisible. You can preview each of them by selecting it in the Landscape Masks helpers. The landscape already looks good. However, the data density is not sufficient for close-up views. To solve this issue, we're going to add details, texture overlays to the landscape terrain. The corresponding section lists all the landscape masks. You can add the desired number of details to each of them, up to 1,024 in total. Double-click a mask or a detail to rename it. so the detailed with the default material was applied according to the debris mask. The detail parameters enable you to apply additional masking. Please keep in mind that all changes made to details require the graphic data of the landscape terrain object to be reloaded, so details are not to be modified at runtime. You can adjust the mask threshold and contrast. It is also possible to apply masking by color of the base albedo texture. Just pick a color and make sure the alpha value is non-zero. Masking by height is useful for defining height-dependent areas, for example, snowy peaks of mountains. Here you can define the minimum and maximum visibility heights and fading values. The default detail material is read-only, so let us create a child material and call it debris detail. The visual appearance of the detail is defined by albedo, roughness, and height textures. Use the size parameter to change the size of texture tiles, and contrast to define mask sharpness per material. While the albedo texture has 3 channels, the roughness and height maps are both single channel. The terrain surface is subject to adaptive hardware tessellation and displaced according to the specified height map. You can control the displacement height via the scale parameter. The additional mask is very useful when it comes to blending several details together. Specify a grayscale mask to modulate the base landmark mask, making the detailed area more or less dense. Various results can be achieved by choosing different blend modes for the additional mask. In the multiplicative mode, the landscape mask is multiplied by the additional mask, so the detail area shrinks. The overlay mode gives similar results with higher contrast. In the additive mode, the additional mask is added to the landscape mask, and therefore the detail covers the whole landscape. The last mode, vivid light, preserves the additional mask pattern only on semi-transparent pixels of the landscape mask, which can be an option for a jagged transition. Tiling of detail textures is inevitable at large distances. To reduce it, we can add a copy of the detail and apply complex masking. Create a child material so as to keep the common parameters and textures. Let these details represent coarse and fine details respectively. For the coarse detail, we increase tile size, and let the fine one have similar tiles. Changing the mask's blend mode to overlay helps blend these details. You can also play with the opacity parameters to get the desired result. The last thing is that the coarse detail should have a greater height scale than the fine one. Well, these manipulations have reduced texture tiling. Please note, all these settings are suitable for this particular example and may vary as they depend on the look of detail textures and the landscape feature. When necessary, you can reorder details by using the arrow buttons or via dragging. You can also drag details to another landscape mask. When configuring details, you may face a situation when landscape masks overlap each other. Here, for example, the grass detail covers the debris. Use arrow buttons or drag the landscape mask to another place to reorder the masks. Note that this doesn't mess up the source mask's data. You simply change the rendering order for the details. By default, detail textures are mapped using linear UV mapping. That's why the textures appear stretched on steep faces. But you can enable triplanar mapping to selected details. Hold the Control key to select many. Use the Blend Triplanar parameter to control blending of mapping planes. The more details you add, the more diverse look of your terrain you get. You can make use of screen space shadows, cast from small objects to improve visual consistency. Enable this feature in the Rendering Shadows menu and in the Sunlight parameters. Well, the detailed landscape looks fine. Let's add a cloud layer to make the look of our scene even better. Details can be fine-tuned using the brush editor. You can paint on any landscape mask to make certain areas more or less visible. Keep the white color, choose the desired color intensity. Adjust the opacity with the Alt plus mouse wheel hotkey. The surface is being displayed immediately in accordance with the visible details. When editing landscape masks, pay attention to the Mask's Override option. When enabled, it forces the selected landscape mask to be visible regardless of whether it is hidden by overlapping masks. That's how the brush marks are added to the selected masks and subtracted from the masks above. Turn this option off to modify only the selected mask, preventing unexpected changes of other ones. Free your creativity in blending multiple details. Please keep in mind that the density of brush marks is fixed and depends on the current data density of the landscape layer map. Re-importing the graphic data resets all manual layer modifications, so it's much more convenient to make use of the layer system. Create a new landscape layer map, place it at the desired location, and create a landscape asset for it. This is going to be our layer with manual modifications. Set the data filling mode to manual. By default, the height map, albedo, and masks are alpha blended, thus overriding the data of the base layer. Let's set the height map blending mode to additive. As you see, re-importing is not performed on changing the blending modes. From now on, the height map will be added atop the base layer. Let's also set the albedo blending mode to multiplicative mode to make the albedo color of the base layer unaffected by the white color. Now you can modify height and masks data the way you need on a separate layer. The great point here is that the layer can be later transformed for fine adjustment. Now modifications are separated from the base layer so you can freely disable them or update the terrain graphic data. Landscape Layers is a powerful system available out of the box. You can import textures representing a part of the terrain surface to create an inset with higher data density. Use the opacity mask for the height map and albedo. Choose the mask channel, alpha in our case, so the borders of the inset are blended seamlessly. As for the landscape masks, you can disable the ones you don't need, or keep them untouched, since the default color is black and the alpha blend mode is selected. Click Re-import, and now we've got an area with a higher local data density. The order parameter defines the sorting order for landscape layer maps overlapping each other. A layer should have a higher order value to be rendered atop the other one. If your world contains several landscape layers, one which represents the basic shape of the terrain, such as our base layer, while others are used as insets placed within the bounds of the base layer and having an insignificant height difference from the base layer, pay your attention to the culling flag. This option is essential for streaming the landscape data, as it enables loading of preliminary low-detail data of the layer to define which areas of the landscape are visible and should therefore be loaded. So, to reduce the CPU load at world startup, it makes sense to disable the culling flag for inserts and leave it enabled for the base layer. By default, collision and intersection detection for landscape layer maps is enabled. If your project requires physics simulation or detection of intersections with the terrain surface, make sure the corresponding options are enabled for the landscape terrain surface. Here you can also define the corresponding bit masks for selective collision and intersection detection. Intersection and collision settings of the landscape terrain object are available for adjustment on the Node tab. Intersections are detected with a variable precision, starting from a lower value and ending up with a higher one. Normally, there is no need to change these values. However, in case of detection errors, you can tweak the precision parameters, as well as enable bicubic filtering of textures for optimum balance. Be careful, as it may significantly affect performance and accuracy. Also, make note that details don't participate in collision and intersection detection, so it is not recommended to imply intense displacement using details, since visual inconsistency may appear. Independent Layer System makes the landscape terrain friendly for collaborative editing using version control systems. Each of 3D artists in a team can work with a separate landscape layer and contribute to the development of the whole landscape. This will require certain preparations in your world. Create a new node layer and specify where to save its asset. This node type represents a subset of world nodes stored in a node asset. Place the node layer in the origin for convenience. Now you can make a separate landscape layer map child to the node layer and save it after making any changes to the landscape layer. After that, you will only need to commit the modified node layer and the landscape layer map asset using your version control system. Upon checkout and world reloading, the changes will be applied and visible on workstations of other team members. Layers can be used for runtime modification of the terrain surface as well. Let's create a crater, for example. In the Asset browser, click Create Landscape Layer Map and specify some crater textures. Let's set the minimum height to -100 in order to make a deep crater. Use a smooth circle texture as the opacity mask and choose the Additive Height Map Blending mode. Then repeat almost the same actions for the albedo map and re-import. You can simply drag a landscape layer map asset right to the viewport to create a landscape layer quickly. Let's make it 100 meters across and adjust the height scale. Now we can save the crater to a node asset by dragging the node to the Asset browser and having it as a node reference. This enables you to instantiate your crater either in UNIGINE Editor or at runtime via code. Let's consider an example of a vehicle leaving traces. We can prepare a small layer map representing a chunk of a wheel trace. It doesn't have a significant impact on the height map and is great for a wheel trace. You will need to implement some simple logic of spawning chunks behind the wheels of your vehicle. A large number of spawned layer maps is not going to have a significant impact on performance. However, it is much better for memory to destroy unnecessary traces at a certain distance. Performance of such runtime modifications is determined by the data density and streaming settings. Let's consider the global landscape terrain settings. Choose Windows, Settings, then Landscape section. For your convenience, optimized landscape terrain settings are available for each of the default render presets included in your project's template, from low to ultra quality, including the separate one for VR applications. Double-click the asset to apply a corresponding preset, or you can choose it from the list. The settings include geometry, streaming, culling, and cache parameters. Let's take a closer look at them. The Holes option is responsible for decal-based holes in the terrain surface. Enable it if you need to cut out an area of the surface. Other geometry settings control the landscape terrain tessellation. Let us enable the Object Wireframe helper to see the effect better. Keep in mind that changing some of the settings here causes the landscape terrain object to reload all its graphic data, which is unacceptable at runtime. Some parameters can be changed without reloading. The geometry progression parameter defines progression of geometry tessellation with the distance. Higher values result in more polygons tessellated, affecting the performance. Geometry fade LOD stands for intensity of fading between tessellation levels. Use the geometry subpixel reduction as a size threshold for too many polygons that should be removed. This is how you can quickly increase and reduce the complexity of landscape terrain geometry. The geometry polygon size parameter controls the maximum allowed density of the geometry measured in meters. The value of 1 meter flattens the surface and reduces all possible tessellation details. The value of 1 centimeter is enough for a good look. Via the visibility distance, you can control the visibility of terrain polygons at a distance from the camera. Landscape terrain graphic data is too large to fit in video memory in its entirety, so it is decomposed into smaller chunks, tiles. Asynchronous streaming of these tiles makes it possible to load and render only necessary data at a full level of detail, regardless of the camera's field of view. Flexible streaming settings make it possible to configure terrain rendering even for computers with a limited video memory capacity. You can enable visualization of tiles being streamed using the Landscape Terrain VT Streaming Helper. Individual tiles are asynchronously loaded into the landscape terrain virtual texture, if currently seen by the camera, from the lowest to the highest available MIPMAP level. To preview the content of the landscape virtual texture, enable the Render Textures helper. It has 3 components: albedo, normal, and height, based on which the terrain is rendered. You can see how tiles are drawn into the virtual texture as the camera moves. To estimate the video memory consumption, enable the Rendering Performance Profiler, available in the Tools menu. The Texture Memory Size parameter enables you to control video memory consumption by choosing the size of virtual texture components. With the highest value, more tiles can be cached, but this will require more than 3 gigabytes of video memory. With the lowest size, the virtual texture requires less video memory, but doesn't provide enough capacity for high detail MIP levels, resulting in poor performance, low detail level, and fast flickering of the landscape terrain surface due to continuous reloading of tiles. By adjusting the detail level by angle, you can control the MIP level offsets. for texels of detail textures on polygons facing the camera at a low angle. The tiles update per frame and the tiles load per frame parameters control the number of tiles loaded and passed to the virtual texture each frame. It's better to increase these values for multi-core systems since lower values results in slow loading tiles. The tiles reload per frame parameter controls the number of tiles to be updated when something changes the loaded surface of the landscape terrain. For example, when we transform a landscape layer map, all affected tiles are reloaded on demand. You can check this number in the Rendering Performance Profiler. The Terrain Reload Bounds counter shows the number of unprocessed events causing some area of the surface to be restreamed. It's obvious that smaller changes affect less tiles and are processed much faster. Yours should make sure the counter values reach 0 successfully without bottlenecks. The Terrain Detail Textures counter shows the amount of video memory used by detail textures. You can control the resolution of composed details using the corresponding settings for albedo, height, and additional mask, respectively. Texel size works the same way as the geometry polygon size parameter but affects the density of all graphic data components. You can achieve sub-millimeter details here, provided that you have appropriate data sources. This value is compared to the geometry polygon size, and the highest value is used. Target resolution is an important setting defining the maximum allowed screen resolution used to render the landscape surface. Lower values make most details lost at a distance. Texture filtering defines the quality of filtering between adjacent MIP levels of the render textures. Choosing low and medium modes may result in a noticeable edge between the MIP map levels. Culling parameters provide additional optimization techniques such as backface and frustum culling. In case of culling artifacts on steep polygons, you may need to disable the culling aggressive option. Before being passed to the virtual texture, landscape tiles are cached in the memory. Cache settings are responsible for the amount of memory cache in percentage of the total memory. The more the CPU cache size, the faster intersection and collision detection is. Overall loading of tiles is faster. The GPU cache contains graphic data of tiles to be transferred to the GPU for rendering. If you modify a layer map via the brush editor or your project implies runtime terrain modification, increase cache memory limits and cache lifetime for better performance. Landscape Layer Map is designed as a shared data pool that can be used by other objects. For example, mesh clutters to scatter identical objects such as trees across the world and grass objects to simulate grass and tree imposters. These objects have the mask terrain parameters enabling you to select the desired mask to be used. Let's choose the grass mask. So all the objects are now scattered only across the area of the grass mask. Landscape masks can also be used as land classification masks in your application's logic. You can trace intersections under the mouse cursor or an object to pick the mask value describing the underlying surface. For example, you can implement land cover dependent friction simulation, setting specific values for asphalt, ice, mud, and more. For more details on landscape terrain operation and settings, refer to our online documentation.